Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. As we've been doing over the past few lectures, a number of lectures as a matter of fact, we've been looking at this state space representation of dynamical systems, and we've seen certain important things such as how to realize these state space systems in various forms. We've seen some relation between different state space realizations that arise from the same given transfer function, and we've seen that if there is a similarity transformation from one state space realization to the other, and from the second to a third, then there's also a similarity transformation that exists between the first and the third. In more mathematically precise terms, we can call this the property of transitivity, right? So the property of transitivity is as follows: if the relation between 1 and 2 is the same as the relation between 2 and 3, then the relation between 1 and 3 is the same as both of these, right? So for example, if there's a state space similarity transformation between realization 1 and 2 and between realization 2 and 3, then there's also a similarity transformation between realization 1 and 3, right? And we've also seen how to realize them using op amps, right? Op amps realized as integrators, adders, constant gains, and so on and so forth, all right? We've also taken a brief journey into this domain of linear time varying systems, and in order to see how the connections are between the so-called matrix exponential, which we saw in the context of the solution to a state space equation for a linear time invariant system, and the so-called state transition matrix that arises when we try to solve this linear time varying system. We've seen that we can go from the linear time varying version to the linear time invariant version if we just assume that the system matrix A, yeah, is constant. That is, we can go from this state transition matrix to the matrix exponential if we just assume that A is a constant matrix, doesn't vary with time. Right? We've seen all these connections, and hopefully by now you're clear on how they arise, and note that the results that we used in order to derive certain properties of the state transition matrix, they carry over naturally to linear time invariant systems, and therefore are also true of the matrix exponential. Properties such as the state transition matrix is never going to be singular, yeah, carries over for the matrix exponential as well, which is to say that the matrix exponential will also never be singular. Now if you try to prove that the matrix exponential will never be singular by looking at the matrix expansion, that infinite series, it might not be very straightforward, okay? But on the other hand, the way we saw this state transition matrix was cooked up using the fundamental matrix, that result became pretty apparent, yeah? The only catch is, of course, we have assumed that the solution is unique, right? We haven't proved that because that will take us into the domain of, as I said, mathematical treatise on ordinary differential equation. We are not interested in doing that for the purpose of this course. So we'll just go with the assumption, which is indeed true, that the solution of a linear time invariant system, or even for a linear time varying system, if it satisfies this so-called Lipschitz condition, yeah, it can be shown that it's going to have a unique solution. Right? So now today we are going to address the really major critical issue which we bothered ourselves with when we dealt with transfer functions, that is one of stability. So one of the first results or first tools we assembled in our toolkit, if you recall, while studying transfer functions was this Routh-Hurwitz criteria. And what did this talk about? Well, quite simply put, it just told us when a particular polynomial had all its roots on the left half plane, or when a certain number of them were there in the right half plane as well. Why are roots on the left half plane important? Quite simply because we saw that if the poles of a system yeah, which is represented by a transfer function, if the poles of that system were all on the open left half plane, the system would be considered to be stable. Yeah, what sort of stability? Well, we didn't make it very precise, but now we will. So we call that bounded input, bounded output stable, or BIBO stable, right? So in dealing with state space realizations, we want to go beyond this notion of BIBO stability, because as we've seen, this transfer function only gives us some external description, right? We are more interested in internal descriptions, and that is the motivation behind moving into this state space realm. But before we go into that, here's a small exercise for you, which is probably carried over from the last day's lecture. We've already seen what the solution of the homogeneous linear time varying system is, represented in terms of the state transition matrix. So here's an exercise for you. So try to prove that. So you'll have to show that xt given by phi t comma t naught times x at t naught plus integration from t naught to t phi t comma tau b tau, it would be, we are integrating with respect to tau now, the running variable is tau, u tau d tau, okay, is a solution of the state equation given by x dot is equal to at xt plus bt ut. Okay, so you have to show that this is indeed the solution, where of course, well, let me just make a small change here. I'll just call this not xt naught, but I'll just call it x naught, and I'll just say that xt naught is equal to x naught. Okay, so you have to show this. Of course, if you've been following the previous lecture closely, you would immediately see the tool that you need to prove this. It's basically that differentiation under the integration sign by Leibniz rule. If you use that, you should be able to immediately show this. But do take this exercise and try to see, because once you're able to prove this, it will convince you that yes, you've actually grasped the material we've covered in the last lecture or last 1 or 2 lectures or so. Okay, so now that we are through with this, let us jump into this notion of so-called stability. Okay, right. So let me just say what this notion of BIBO stability is, which we are familiar with. Maybe we haven't mentioned it by this name, but what BIBO stability says is that I'm going to do it very loosely and not very formally. So if the input say r of t is bounded, that is RT is less than or equal to some m, yeah, for all time t, yeah, t greater than t naught, greater than or equal to t naught, and less than infinity, yeah, then the output is also bounded. Okay, let me give the output some variable. So then the output y of t is also bounded, that is we will name this another variable, y of t is less than or equal to m tilde, okay, for all instance of time for which we are interested in the solution of the system. Okay, so remember, of course, we need to mention that m and m tilde are finite. Yeah, that's a given. So it basically says that if you have a system in which you are giving as input this input signal RT, you get an output signal yt, which will also remain bounded. So if the input is bounded, it need not necessarily be that they are bounded by the same quantity. That is why we've generalized it and we've called it m and m tilde. Yeah, but provided the input is bounded, the output would also be bounded in such a BIBO stable system. alright. So this is essentially the notion of a Bibo stable system, right. So what sort of signals can we think of that are bounded? Well, for the input at least, well, we can say that, you know, something like a step, something like maybe even a sinusoid, the decaying sinusoids, the decaying cosinusoids, yeah, any function that the exponentials, these are all bounded, right. There's an upper bound. Any signal that has an upper bound, there is a maximum value that it attains over the time interval of our interest, yeah, that's bounded in that interval. Now here we are extending that interval to infinity. So it's from the initial instant t naught till infinity. If it's bounded, then well, it's a bounded signal, and that qualifies as a candidate input. Now you apply that input to the system and you check whether your output is also bounded, right. So your output also has a maximum value below which it takes up values for all instants of time from t naught to infinity, right. So that is the notion of Bibo stability, but clearly you would see the flaw in this. Recall that right at the beginning of our discussions of state space systems, we took up this example and we saw that, well, you know, this is only concerned with the external input. So again, to reiterate, we had this system where we had this 1 by s plus 1, I guess it was s minus 1 by s plus 1, sorry, it was s minus 1 by s plus 1 connected in series with cascade with 1 by s minus 1, right. Now insofar as the input, or rather, you know, let me call this, okay, let me make this ut, yeah, that makes it better, call this ut, because that's what we've been using for quite some time now in state space, okay. So let's say this is u of s and this is y of s. Now quite clearly, if you look at it as a transfer function, you would see that the transfer function is, well, 1 by s plus 1. So you give any possible bounded input, yeah, and you expect that the output would be bounded. But this doesn't account for the fact that there could be non-zero initial conditions, right, because this is only concerned with the externally applied input, which is u. So that's why it gives you an external description of stability. But we've clearly seen that if there are some non-zero initial conditions here, yeah, if there are some non-zero initial conditions here, then it will always blow up, right. So even in the other case, when we flipped the order of these two blocks, yeah, we saw that there were only certain conditions subject to which this would remain bounded. If all the initial conditions were all 0, or maybe the initial condition met some very stringent condition, yeah, such as that they satisfied, they lay on a straight line in the x1 x2 plane. Just go back to that example we solved quite explicitly many lectures back and you will find out, right. But that's in general not going to be true. If your initial conditions are non-zero, yeah, you might expect this to blow up. So this Bibo stability, even if the system is Bibo stable, yeah, we have seen that the output could blow up. So therefore this Bibo stability seems like it may not be very useful to us. Now of course one of the conditions is that I mean, you can immediately see that may not be very useful as such, this notion of Bibo stability, but well, this definition is even harder to check, and in fact let me give you the technical definition a bit. So formally, well, we say that if or rather it's an if and only if condition. So let me say system is Bibo stable if and only if. So if means it's sufficient, only if means it's necessary. So it's a sufficient and necessary condition that the impulse response, remember that old fellow we had encountered right at the beginning, the impulse response of the system h of t, say we denote it by the h of t, yeah, is absolutely integrable. Yeah, what does absolutely integrable mean? We'll write that example. So what is this notion of this absolute thing? Well, absolute means it's the absolute value, okay. So absolute value means it's basically what we in common parlance call the modulus. So when we say something is absolutely integrable, it means that even if it assumes positive and negative values, so h of t for different values of time could take up both positive as well as negative values, alright, but we will only be taking the positive value. So we will be considering, so basically this mod of h of t is equal to h of t if h of t is greater than 0 is equal to minus h of t if h of t is less than 0, yeah. So we say this is absolutely integrable, that is we will take this, okay, or absolutely integrable over 0 to infinity. So that means that, what does this notion of absolutely integrable, of course you can integrate anything, right, but when we say it is absolutely integrable, it means that what the result of that integration, yeah. So it is very important that you define, you might say what is this integration, I have x squared, I can integrate it, yeah, it will be x cubed by 3 and then I just apply the limit, improper limit like this improper integral extending to infinity and I get infinity. So what do you mean by absolutely integrable? Absolutely integrable means that not just you can integrate it, but the result of that integration must be bounded. So what we are saying is that this h of t dt, it better be bounded. So I have already used m and m tilde, let me call this m bar, yeah, no relation between the earlier loose definition and this somewhat more formal definition, yeah, and of course this has to be finite, this has to be a finite quantity, right. So this is what it says, that if your impulse response is absolutely integrable, then the system is Bibo stable. Now notice, by its very nature, what is this impulse response? Impulse response can only arise out of the application of some external input. Unless you apply an external input, the question of impulse response does not arise. We have also seen, notice, that we can cook up any signal as a train of impulses, right. So therefore, if we consider in the context of linear time invariant system, you take up any input that is that can be cooked up as a train of impulses, and then if you, for example, take up say some g of t is equal to, let us say, some summation of delta, yeah, delta I going from 0 to or 1 to infinity, whatever, right, some alpha I, yeah, and times some delta, yeah. So these are of course the way you remember we cooked up the signal, that was very beginning, right, the very beginning of the course, right. This is the way you also split up a function for Riemann integration and things like that, okay. So you must have been familiar with these sort of things, yeah. So this is what we are trying to say here, yeah. So we then cook this up and then we let this delta go to 0. So as delta tends to 0, this delta I tends to the Dirac delta, yeah. So basically we can approximate a signal as a train of impulses, and then if we want to find out the response due to gt, all that we need to do is need to find the response due to each individual impulse. So alpha I times the delta, then alpha I plus 1 times the delta, right. So it's just a sum of these impulse responses, yeah. So if the impulse response itself, some of these weighted impulse responses, so if the impulse response itself is bounded, then the sum of this weighted impulse response will also be bounded, and therefore this is the notion of this Bibo stability, which has everything to do with an externally applied input and nothing to do with the initial conditions at all, right. So this is very important, because this is exactly the lacuna, the drawback of the transfer function domain that we are trying to now address with our new notion of the state space, and we shall slowly see that that's why we come up with a new notion of stability as well, yeah. So notice the important thing that I just stopped short of saying in the last slide, that what is after all this impulse response? This impulse response is basically nothing but the inverse Laplace transform of the transfer function. So to say that the impulse response, well, is going to be bounded, yeah, is the same as saying, after all, if you take the Laplace inverse of the GS, of the transfer function, what sort of functions are you going to get? if you take for example the linear time invariant system for which Laplace transforms are applicable, and you consider rational transfer functions, so no time delay terms and likewise, then of course your impulse response would contain terms that are of exponential nature, exponential functions, right. So the functions will be exponential in nature. Of course these exponentials could be purely real or they could be complex numbers, but even so, let me make that precise here. For again, I am not getting into the very details, for that you might have already done some courses on signals and systems to familiarize yourselves with it, but at least loosely speaking you understand what I am saying here. What I am saying is that, well, this h of t is nothing but the Laplace inverse of well, I have called it g of s, but you can call it h of s, which is the transfer function. Sorry about the notation, you can replace this h of s with g of s if you like. I am just, from h to h is easier, rather more obvious, so that is why I am calling the transfer function h of s now. Earlier I used to call it g of s, even 2 slides back I called it g of s, but yeah, it is just a symbol, right. So what we are saying is, what sort of a transfer function is this? This is a rational transfer function, so essentially this will be ultimately of some form like 1 by s minus alpha 1 plus 1 by s minus alpha 2 plus maybe somewhere you have this s square plus 2 zeta 1 omega 1 s plus omega 1 squared, yeah, and some beta s plus gamma, like so, some terms like these only, right, and then you can individually apply the Laplace to each of these, yeah, Laplace inverse to each of these because of the linearity of the Laplace transform property, yeah. So then each of these, what are these going to contain? Some weight times e to the z1t, or rather not z, let me call them p1t, the poles, right, e to the p1t, e to the p2t, some, I do not know, what should I call it, not alphas, maybe I should have called them p1, p2 here, yeah. So then I can use the alpha here, yeah, now I can use the alpha here. So this is some alpha 2, likewise you can have for these complex factors, you can have like e to the minus zeta omega n t, some cos omega n t, e to the minus zeta omega n t, some sine omega n t. So these are all the types of terms, yeah. So even though I am saying it is pretty loose, this is actually pretty exhaustive, comprehensive. These are all we have seen from our understanding of Laplace transforms and their inverses. We have seen that for rational transfer functions, this is all there is to it. So now, with this in mind, with this sort of a function in mind, when is this absolutely integrable? Look, if they are exponential functions, yeah, what sort of exponentials are absolutely integrable? Or if they are sinusoids and cosinusoids, if you just let them be, yeah, if you take just the sinusoid and the cosinusoid, you will see that because they oscillate, yeah, they are going to just accrue together, yeah. So this is the crucial bit here now. So if you have real numbers p1, p2, then they better be negative, right, these better be negative, because if they aren't negative then they are going to blow up, and that integration, you have no hope for this integral to be bounded, right. Now what about these terms? So let me mark them out for special treatment here. What about these terms? As long as the real part of these poles, that is the zeta omega n, yeah, as long as the zeta omega n is positive, so the damping is basically positive, yeah, then even though this sinusoid and cosinusoid might oscillate, right, they are damped sinusoids and cosinusoids, so that will also be absolutely integrable. If they become negative, they are going to meet with the same fate, they are going to blow up, although in an oscillatory fashion, so you have no hope. What happens when, so this is the interesting bit, what happens when this zeta omega n is equal to 0? So that means you have poles that are purely on the imaginary axis. Well, that now is a bit tricky, yeah. So suffices to say that, well, we have talked about this earlier also, that if you have a impulse response for which, or if you have a transfer function for which any bounded input takes you to an unbounded output. So let us see how this is consistent with it. You take this one. So take this u of t to be exactly a cosinusoid of the same frequency as the system's pole. So what I am saying is, suppose you have 1 by s squared plus omega squared is equal to your h of s, and let us say you apply the u of s also to be equal to 1 by s squared plus omega squared. Yeah. So you agree that this u of s is bounded, I mean this u of t, yeah, let us say this is omega squared. So this is probably, if I am not mistaken, if I have not forgotten my Laplace table, this is cos omega t. Yeah. Now notice that taken in and of itself, this is obviously bounded. This is always going to be less than or equal to 1. So this input is bounded. But what if you apply this to this transfer function here? I think it, yeah, I think this should be omega or omega squared. Anyway, it does not matter. So, or maybe omega squared, I do not know, should it be? Anyway, you check that please, whatever, it is omega, omega squared, whatever, but the point is that this u of t is going to be bounded. So this is a bounded input, remember this is a bounded input. But now if you apply it to this transfer function, what you end up getting as a resultant is this y of s becomes repeated poles, s squared plus omega squared whole squared, right, and what does this lead to therefore? So this then tells you that this y of t, yeah, if you have repeated poles, it will contain some t times this cos omega t, right, and that is a problem because now you gave a bounded input but you got an unbounded output. So therefore this Bibo stable system, for that the requirement is that all your poles better be on the strict left half plane, not even on the imaginary axis. And this is also consistent with this formal definition, because you see you take the cos omega t, if you did not take the absolute value, then over a complete time period the integral would be 0. But now you are flipping it. So basically your function, yeah, it would be something like this. This is going to be your mod of ht, the absolute value of ht is going to be like this, and you keep integrating this. See, this never settles down. So if you go from t is equal to 0 till t gets to infinity all the way, this sum is going to always accrue, it is going to keep adding more and more, more and more. So it is never going to be bounded by any quantity, right. So this fits in with both of these definitions, and therefore what we say is that for Bibo stable systems we only talk about the transfer function, and what we say is that the transfer function better not contain any poles on the closed right half plane, or better have all its poles on the open right half plane. Closed means it includes the boundary, boundary is the j omega axis. So if you have any poles on the j omega axis or on the right half plane, then it is not bounded input bounded output stable. If you have all your poles on the strict left half plane, then and only then it is going to be Bibo stable, yeah. But that is all within the context of transfer functions. So this was some sort of a reprisal of what we have already seen. I guess we had already discussed this somewhat earlier, but this is a little more formal approach, a little more formal definition. That is why I introduced this absolutely integrable, this notion of absolute integrability, yeah. Alright, but this clearly does not suffice, as you know, I reiterate, as we had already seen in case of this, where was I, yeah, in this system here. We started, one of our strong motivations, yeah, was this. So what did we see here? Well, we saw that in this case it was not the input that was the culprit. Even if the input was bounded, the output still went unbounded, and that was primarily because you had some non-zero initial conditions which messed around. Not just non-zero initial conditions, to be more precise, what happened here was that there was this pole zero cancellation. Due to this pole zero cancellation, what was not apparent in the transfer function. So again, let me split that up into bits. Probably I am going a little too fast. Here is what happened. You obtained a transfer function by coalescing these two blocks, by cancelling the pole and the 0. Then you applied an input, considered 0 initial conditions, and you guessed that because the transfer function is, the poles of the transfer function, or the pole of the transfer function is in the left half plane, I expect the output to be bounded. But what happened is, when you connected the circuit, the system's fuse blew up. Why would it happen? Well, not because of some fault in the input, not because the input was unbounded, not because your analysis or your notion of Bibo stability is flawed, that is clearly correct because this is what it means. But then something was at play here, some mischief was at play, and the mischief was in the form of two things. One, we did not consider, I mean the non-zero initial condition is not the mischief, non-zero initial conditions happen all the time. The thing that we missed, maybe not mischief, but the thing that we missed was that we did not account for this non-zero initial condition. The transfer function based classical approach does not allow us to account for this non-zero initial condition. Yeah, so we missed one trick there. But even so, it might still have sort of stabilized. What prevented it from stabilizing? Well, the fact that you had one pole which was in the right half plane, and here is the mischief, it got cancelled. So therefore this unstable pole did not appear, did not make its appearance in this transfer function. So we completely missed its presence. Look, even if the initial conditions were non-zero, but if this cancelled out pole was in the left half plane, your notion of stability would not have been shaken to the core, okay. But it is because of so many of these things coming together. What are the three things? One, for one, there was this non-zero initial condition which was not accounted for. Second, there was an unstable pole, okay. Third, this unstable pole was cancelled. If any of these conditions, I urge you to think about it a bit, if any of these three conditions were not to be true in this, the response might have been unexpected, in the sense that the response due to the zero state and the response due to the zero state plus zero input will be different, yeah, because in one the zero input response is also being added. So the response would have been different, but at least the notion of stability would not have been jeopardized. So what jeopardizes the notion of stability? What leads us or what motivates us to look beyond the notion of Bibo stability is what I am trying to say. You have this typical case when there is non-zero initial condition, there is an unstable pole which somehow internally got cancelled, alright. So these three things taken together revealed to us the inadequacy of this Bibo stability notion, yeah, because Bibo stability will tell us that all is perfectly well with this system insofar as stability goes, but we know that it is not true, yeah. These three things combined together can bring us to a junction where we will find that, well, the system is not going to be stable, the desired behavior, that is the system's output should not blow up, is not going to be true anymore. So what could be one way of circumventing this? Well, a very commonsensical logical approach would be that you do not cancel this. So let us say in a practical system you have a system 1. So look, after all these block diagrams what we draw are just some theoretical artifices, right. But in a practical system, this is system 1, this is system 2, likewise you have say system R like this, yeah. So one of the assumptions we make is within the model, that is the transfer function of system I, there is no pole 0 cancellation on the right half plane. So what I am saying is essentially if this is G1, if this is G2, if this is GR, yeah. So if there is this G1 and let us say this G1 has this S minus 1, S plus 2 like this, S plus 5 something like this, and S minus 1 into S plus 8, S plus 700, I do not know, S plus 10,000, whatever it is, yeah. So if there is this thing here, you better not cancel out these fellows. either such things will not arise, but if such things also arise, then you better not cancel out this fellow. Now you might say, well, if I just have this s minus 1 by s minus 1, yeah, which is essentially 1, how do I realize this? Well, we assume that such weird crazy things do not happen. So what we do is we then just multiply this out and we get this as a numerator polynomial, we multiply this out, we get this as a denominator polynomial, and we realize it using one of those op-amp realizations that we have seen right at the beginning. So you get to this G1, get to its state space realization. From this G2 similarly, you get to its state space realization. From this G3 similarly, you get to its state space realization, okay. And now you have to now consider that, well, maybe I am not cancelling out poles between that are inherent to the system, or maybe such things do not arise, okay. So for our sake, for our problem's sake, let us just assume that internally at least there is no such unstable mode that is cancelled, because if it is after all some hardware component. Just remove the components that are responsible for this, you can always fix it, yeah. So I mean, this is within your hand. If you have been given a access to the interior of a box, it is no longer a black box for you, right. So unless it is a very ill designed system, you can always avoid these scenarios, yeah, some funny scenarios like this, right. You can always avoid these scenarios where you have this same pole and same zero within a same system, yeah, it is just some manufacturing thing, right. So get rid of such cases. So we consider that we will not encounter this sort of a weird scenario within a particular GI. But remember, when you are interconnecting systems, there is absolutely no guarantee, you might say it is improbable, but not impossible, right, that there are absolutely no guarantees that there is no cancellation between a 0 of system GK and a pole of system GJ, yeah. So these systems have come independently manufactured. One might be an electromechanical system, one might be a mechanical system, one might be a I do not know, any kind of a system like a nuclear reactor, yeah, it could have different types of systems, right, and their poles and zeros could arise from different physical manufacturing processes. So there could be cancellation between them, right. So how do we ensure that this cancellation is not happening? Unfortunately, if you are just taking the transfer function G1, G2, G3, you might avoid this scenario because of this assumption. So you might say that, well, I haven't manufactured a system where this s minus 1 and s minus 1 are both there in the numerator and denominator, yeah. So I never encountered such scenarios within this one particular block, but who is to say that if you are putting these blocks together, yeah, that there won't be such cancellation. So then again this transfer function domain is inadequate here, yeah. So that is why we go for this more sophisticated notion of what we now call as this asymptotic stability, or somewhere, some cases you will also find this as internal stability. So we call it internally stable. So this is the notion of internal stability. So what does this notion of asymptotic stability or internal stability tell us? Well, quite simply put, I will not again define this formally. So here for asymptotic stability we do not consider the external input at all. So we say if, and you will see that even if we do not consider this external input, it turns out that asymptotic stability will always imply Bibo stability. The other way is not true, as we have clearly seen. Well, for that we need to know what asymptotic stability is. So what we are saying is, if we consider the homogeneous case, homogeneous system x dot is equal to Ax, yeah, with x t naught is equal to x 0, yeah, and we have x of t. So I will explain it in a while what this means. Goes to 0 as t tends to infinity for all x naught in Rn. Okay, what does this mean? what is this, first of all we have to understand this piece by piece. What is this thing that I have defined here, like this weird symbol? You might have encountered this earlier. This is basically the norm. In fact, to be precise, this is a 2 norm. So if you have a vector, 1, 2, 3, 4, yeah, then its 2 norm, would be defined as square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. Yeah. In general, the pth norm of a vector would be, so if you have, let us say, the pth norm of this vector itself, if you want to take the pth norm of this vector 1, 2, 3, 4, so it is a fact that all norms are equivalent. Yeah. So if it goes down to 0 in one norm, in the sense of one of these norms, it will go down to 0 in the sense of other norm as well. So this is defined as basically 1 to the power p plus 2 to the power p plus 3 to the power p, actually I should put the modulus sign here, the absolute value, plus 4 to the power p, and this overall thing to the power 1 by p. Yeah, you see now you apply p is equal to 2 and this definition fits in. So that is the 2 norm. At least we have understood what this object is. But what is it saying here? You see, this internal description or this notion of internal stability or asymptotic stability is not bothered about what is happening to the output, or rather what is happening at the input port, the external input, right. It will turn out later, and as we shall see shortly, that even by being completely nonchalant about this input, yeah, we will see that so long as the input is bounded, this asymptotic stability is a broader sense of stability, in the sense that if something is asymptotically stable, it is also BIBO stable. Yeah. So let us get to that, like what is the condition, what is the equivalent condition for this. You see, we have already figured that this condition for BIBO stability, we have to check this absolute integrability, is not very handy. Yeah. So for the special case of linear time invariant system, we got to this condition that, well, the easier way to check for BIBO stability is check for the poles of the transfer function of the LTI system, and if they are all in the open left half plane, it is BIBO stable. So that is kind of convincing, and that gives us an easier way to test. So we want something like that also here also. I mean, this on the face of it looks very complicated. First of all, you have this x dot is equal to ax given an initial condition, then you have to solve for this xt, yeah, and then you have to now say whether the second norm goes to 0 and all. Yeah, I mean, it seems very cumbersome. I mean, there is no real apparent way to check, a quick check. What do you do then? Do you just simulate with all possible initial conditions, yeah, as it says for all possible x0 in Rn. So do you apply all possible initial conditions? Quite clearly that is not feasible, yeah. So how do you check? And suppose it is like a mathematical problem, you do not even have a hardware. Mathematically speaking, how will you check? Would you just compute? If you have an analog computer, you can at least apply some initial conditions as inputs through voltages and check. Now if it is a mathematical thing, would you give all these possible different initial conditions and check? Well, it turns out you need just n linearly independent initial conditions, but even that is too much, right. Why should we go through all that trouble of checking for all these n initial conditions if there is some other more intuitively obvious, not just intuitively, more technically rigorous also, an obvious way of checking for the equivalence of this asymptotic stability. What is that? Well, we notice that what is xt for this system? Xt is going to be e to the at times x naught, right. So therefore, if we are saying that this, we are interested in the second norm of xt, that is equivalent to saying we are interested in the second norm of, oh sorry, this will be t minus t naught, excuse me, yeah. So that is basically like tantamount to saying we are checking for this. So we want to see when e to the a t minus t naught times x naught, this goes to 0 as t tends to infinity. This is what we want to check. If we have found this condition, then that will be the same as the condition required for asymptotic stability, right. So what would that condition be? Notice that we already know again, and now this will make it worth our all the effort that we put in earlier to understand the different forms or different structures of this exponential matrix. We have learned at least 3 different methods. We have seen that one is through this Si minus A inverse, the Laplace transform of that, we can find out this e to the at. Second method was through this general diagonalization or Jordan canonical form, and the third method was when we use the Cayley-Hamilton theorem to derive or to compute this e to the at matrix. In all of these, I will now make a statement and you go back and check in the previous lecture. So look at individual entries of e to the a t minus t naught, yeah, they can only be of the following form. Yeah, this is very similar to the approach we adopted in Bibo stability. Note that in Bibo stability what did we do? We said that, well, when we look at this impulse response, these are the only sort of terms that appear in the impulse response, right. So I want you to see the parallel between the approach that I am following here. Here I am saying that look at the individual entries of this e to the at minus t naught matrix, okay, very crucial to understanding what the equivalent condition for asymptotic stability is, to understand what each individual entry of this looks like. So they can only be of the following form. What sort of form? E to the lambda t when lambda is a real number, yeah, or t to the k e to the lambda t when k is a positive integer and lambda is a real number, or of course there are some constants multiplying them, right. So some alpha times this, some beta times this, some gamma times e to the at cos bt or e to the at. So this is not division, let me not confuse you there, yeah. So this is gamma 1 times this, or gamma 2 times this e to the at sin bt, or if you have repeated Jordan blocks of complex numbers, right, remember. So I will just explain in a while, it will take a minute or two to explain why these are the only forms that appear. Or you have some delta 1 times t to the power k e to the power at cos bt, or let me just use it up here, okay, let me go to the next slide, or you have say this delta 2 e to the at t to the power k sin bt. So these are the only terms, in fact that is all there is. Why? Because remember I am going to make use of the Jordan form here. If you are given an A, there always exists P such that A is equal to P inverse, or rather P J P inverse, where J is the Jordan block, Jordan form of the matrix. So what is the Jordan form? As you recall, the Jordan form could be like either there could be diagonal entries like this, log diagonals like this, or you can have this lambda, lambda, 0, lambda, these Jordan chains like this. Okay, for want of space I will have to erase this, but this is just a repetition. I urge you to go back to all the different forms of Jordan that we can have. Or you can have this sort of a Jordan A, B, minus B, A, things like this, yeah. Or you can have maybe an I like this and repeated blocks of Jordan like this, A, B, minus B, A, things like this, right. These are all the forms. So this form will give you terms like, this form will give you terms like, okay, let me color code it, yeah, so that you understand. So this form will give you terms such as this, okay. Then this form will give you terms such as these, all right. Let me see what other color can I use, okay. Where do these colors come from? Where do these things come from? Sorry, what color was I using? Yeah. So this, where do these terms arise from? Terms like these and these, well, they quite simply come from, okay, I have to erase this again. So this is of course the repeated complex roots, but if you have say non-repeated complex roots, so suppose you have terms like a b minus b a, yeah. So this is just a diagonal real Jordan block, yeah. So this sort of terms would give rise to terms like these. And finally, let us see what other color is remaining. This term, or let us say this term, they arise from blocks like these, yeah. And we have shown that the Jordan form can only be something that looks like this. These are all there are to the Jordan form. So therefore, when you are operating this J, when you are operating this P J P inverse, yeah, when you are applying this P J P inverse on the Jordan form to get the A, yeah, you know that you want to get this e to the at, that will be nothing but P e to the j t P inverse. So therefore, e to the at minus t0 times x0 is equal to nothing but P e to the power j t minus t0 P inverse x0, right. So this P inverse x0, well, of course, so therefore, let me go to the next slide. So therefore, if you want to write this e to the at minus t0 times x0, second norm, that is basically the same as e to the, or rather P e to the j t minus t naught P inverse x naught, right. But this you can call some y. So what is this going to do? This y is basically a vector. So this y is going to take linear combinations of the columns of this e to the j matrix. And what are these e to the j matrix? Yeah, if this is the j matrix, then the e to the jt matrix can only contain terms that are the exponentials of these, which are nothing but terms like these. So you combine them linearly, yeah, and what you get, yeah, are only terms that are of this nature. And then when the p is pre-multiplying them, yeah, when the p is pre-multiplying them, it is basically taking combinations of the rows, right. So eventually what I am claiming is that this will give you a vector like this, of course it is 2 norm. So a vector like this, and these entries here, I am not writing this formally because it will just be too much labor, but you can already see this, yeah, if you look at it a little carefully and closely, you can already see what I am actually trying to say here. So that is why I am not going into the going through the trouble of sort of writing this very rigorously. If I wanted to, I could have done that, but at least I want you to appreciate that the end result of this multiplication is totally governed by terms that are present in this e to the jt. And what are the terms that are present in e to the jt? They are only terms like these. So therefore the end result will also be terms of this form, because after all what you are doing by pre-multiplying by p and post-multiplying by p inverse x naught, yeah, is taking some linear combinations of these terms, nothing else. So what does it require? So if this e to the a t minus t naught times x naught has to go to 0 for t going to infinity, we need, what is the common thread that connects? We need this lambda, this A, yeah, we need decaying sinusoid just like we did for the Bibo stable case, remember? It's the same argument, it's very similar. Only thing, there is something richer going on here. We need lambda, A, what else was there? Yeah, lambda and A are the only symbols I have used to denote these exponentials, right? Lambda, A, etc. to belong to the strict open left half plane. So they must be negative real parts, okay? They must have negative real parts, yeah? But what are these lambdas and A plus JB and all? These are basically nothing but the eigenvalues of the matrix A. That's what the Jordan block tells you, right? The Jordan block puts all the eigenvalues of A on the diagonals, and look, it's only the real parts of these eigenvalues that are appearing on the diagonal entries. So if this A or this lambda or this lambda 1, lambda 2, lambda 3, these fellows, if they have to be all negative real, yeah, if the real parts have to be negative, it just means that the equivalent condition is the eigenvalues of A must be in the open left half plane for system to be asymptotically stable, okay. So that is the condition to check. So if you want to check whether a system is asymptotically stable, you better first figure out, yeah, you better first figure out as to whether all the eigenvalues of the matrix A are in the strict left half plane. If they are on the boundary, then in the notion of this stability we sometimes say it's marginally stable, but as we've seen already, it's not really Bibo stable, right? So we tend to want to avoid those roots on the left half plane. I mean, sorry, in the imaginary axis, if there are poles or if there are eigenvalues on the imaginary axis, then there are some more sophisticated conditions to say whether, okay, there's no hope that this goes to 0, right. So this this system that you're considering here, if your eigenvalue of the A matrix happens to be on the imaginary axis, then it doesn't decay with time, it rather settles to a constant value or oscillates, as you've seen with sinusoids and cosinusoids. So it's not going to 0, but it's still going to remain bounded within some value. So this second norm of x remains bounded, yeah. So at least the 0 input part remains bounded, but if there are repetitions, then things get even more tricky. So then we are forced to look into these conditions of geometric multiplicity and and algebraic multiplicity, and whether the A matrix is diagonalizable or not, that is whether the Jordan block degenerates into the diagonal form or not, okay. So those are the things. If you have, it turns out, so again these are very loosely speaking, I am not going to prove this because again this is going to be involved linear algebra. Asymptotic stability, straightforward case, all poles better be on the strict left half plane, very well understood. I have also proved to you in a very loose fashion, yeah, that it is the condition for asymptotic stability. Marginal stability, it's certainly not going to imply Bibo stability, yeah, but if you are just concerned with the 0 input response, then for marginal stability there is just a single and no repeated eigenvalues on the imaginary axis, well, it may not go down to 0, but at least it remains bounded. If there are repeated eigenvalues on the imaginary axis, then things become a little more difficult to answer. It turns out, and I am going to state this without proof, it turns out that if such a matrix is still diagonalizable, yeah, with repeated eigenvalues on the imaginary axis, if such a system is still diagonalizable, it means that the system is still marginally stable. On the other hand, if it's not diagonalizable, if the A matrix can be gotten into a Jordan form that is not diagonal, then you are in trouble, because then you will have terms like t squared and so on appearing which are not damped, yeah. So even non-zero initial conditions and repeated poles on repeated eigenvalues on the imaginary axis might lead you to instability, not just marginal stability, okay. So that is just a sophisticated notion, but you can actually verify it. It's not very hard to see, but because I didn't want to go into details of the linear algebraic manipulations, I am not going to prove it, okay. But for our purpose we were concerned with understanding what the notion of asymptotic stability is, and we have understood that. Now the immediate consequence of this you should be able to see is that asymptotic stability implies Bibo stability, but Bibo stability need not always imply asymptotic stability. Why so? Well, asymptotic stability means that all your eigenvalues of the system matrix A are on the left half plane, not just left half plane, open left half plane. So therefore it means that determinant lambda I minus A is equal to 0 has all roots on, so asymptotic stability implies this, yeah, on LHP, open left half plane, right. What does this imply? This implies that the poles of GS is equal to, so the GS is given by C times Si minus A inverse B, yeah, given sorry, so this also belong to open left half plane, right. So this is the thread of reasoning, therefore it is Bibo stable, because that is what you need the poles of the transfer function. Now remember that, as I said, if there are pole 0 cancellations, then all the poles do not, all the eigenvalues do not appear as poles of the transfer function. Some of the eigenvalues of A might be cancelled out, okay. So that is the reason why you cannot reverse this argument. So you can say that Bibo stability implies, so let us try to go in the reverse direction and we will see where we hit a roadblock. So we say that Bibo stability implies that all the poles belong to open left half plane. So far we are so good, but the moment we encounter this, we cannot go from here to here. We cannot say that if the poles of this GS are in the open left half plane, it does not imply that the determinant has all its roots in the open left half plane, yeah, because the poles may not be all of the roots of the determinant, yeah, the determinant may have more roots than the poles, right. Some of those roots might have been cancelled out by the zeros of the transfer function. So this is where what prevents us from going in the reverse direction. So Bibo does not in general imply asymptotic stability unless the system is minimal, which is to say that there is no pole 0 cancellation. So if you say Bibo plus minimality or Bibo plus no pole 0 cancellation implies asymptotic stability, but in general just Bibo is not the same as asymptotic stability, yeah. So that is the important notion that we have now discussed. So you see the sophistication in this state space description is we are now no longer looking at just the poles of the transfer function, but rather we are going from the transfer function to the state space realization, and then we are looking at the eigenvalues of the A matrix, okay. So that is how this notion is more sophisticated. So to start with, of course, from transfer function you go to state space realization, and if you already cancelled out the pole and 0, those modes will not be visible in the state space realization. So our fundamental starting point should be the differential equation. Take the differential equation, do not go via the transfer function. So here is what we are going to do, and this is going to be the final point. So you have the ODE, from this you can go to the transfer function, and this will lead you to the notion of Bibo stability check. But on the other hand, if you go from the ODE to a state space realization, yeah, and then you find out the A matrix, and that eigenvalues of the A matrix will give us the notion of asymptotic stability check, okay. So in general, if you ensure that it is asymptotically stable, then this part is guaranteed, alright. But if you have just checked for Bibo stability, you better be careful, you have to still take this route and find out whether it is asymptotically stable. So then obviously it makes sense to go for the state space approach, which is why it is superior. You go for the state space approach, get from an ODE to a state space realization, find out the A matrix, find out its eigenvalues, check if it is asymptotically stable, and then you can also make the tall claim that it is Bibo stable, because asymptotic stability incorporates within itself the notion of Bibo stability. So it is a wider sense of stability, and therefore we have proved another point, we have shown you another reason why the state space realization method, or the classic modern control method of state space systems, is more sophisticated and more preferred over the classical transfer function based approach.